Welcome back to the deep dive. We're here to unpack the core tech in modern industrial control, giving you the insights you need.
Especially for you folks working in mechatronics, dealing with, the really complex stuff like heavy agricultural or construction machinery.
Yeah, those distributed systems where the old centralized PLC model starts to struggle a bit when control logic is spread all over the network.
Exactly. And that's really where IEC 61499 shines, right? It's built for distributing control using these stateful event-driven components.
So today, our mission is laser-focused. We're zeroing in on one of the most, well, fundamental yet surprisingly smart building blocks in that standard,
We are talking about the ECTU.
the event-driven up counter. And look, this isn't just some software counter ticking away in the background.
No. It's really a cornerstone. You use it for sequencing, for safety interlocks, tracking actual physical events, especially across networks that might not always be perfectly stable.
So our plan is straightforward. We'll look at its face first, the inputs, the outputs, what goes in, what comes out.
And then we dive inside. We look at the actual control logic of the ECC and find that specific bit that makes it so reliable, even when pushed to its limits.
Okay, let's start with the basics. What exactly is the ECTU officially?
Right, so the standard, it formally calls it an event function block. That label itself tells you a lot.
Event-driven, meaning it's asynchronous, it waits for something to happen.
Precisely. It doesn't just run on a fixed clock cycle like older PLC logic. It sits there waiting for a specific trigger, an event pulse, before it does anything.
I like that. For tracking something, say fast sensor pulses from a chopper drum or something, you want it to count exactly when the pulse arrives, not whenever the scan cycle gets around to it.
Absolutely. So what events does it actually listen for? There are two main event inputs.
Okay.
First, you've got CU. That's your count-up event input. That's the pulse that makes an increment.
Makes sense.
And the second is R, the reset event input. Pretty self-explanatory that one resets the counter back to 0.
Okay, C to count, R to reset. But in distributed systems, feedback is critical, right? If some other block on the network sends a CU event, how does it know the EC2 actually, did it?
Good point. You need confirmation. So there are corresponding event outputs. For CU, there's CUO count-up output.
Ah, signals and completion.
Exactly. It fires after the counting operation is finished and the internal value is updated. Yeah. And similarly, there's RO, the reset output, which signals that the reset is done.
So those outputs are crucial for chaining logic together reliably. You wait for the CUO or RO before moving to the next step in your sequence.
Precisely. The action isn't complete until that output event fires.
Okay, events tell it when to act. Now, what about the actual data, the numbers?
Right, the data interface. It needs one key data input, PV, which stands for preset value. That's your target count.
The value you're counting towards.
Exactly. And then there are data outputs. The main one is CV, current value. That's the actual count it's holding.
Okay, PV is the target, CV is the current count. What kind of numbers are these?
Both PV and CV are defined in the standard as UINT.
UINT, unsigned integer. So for everyone listening, that means 0 or positive whole numbers, right, up to a certain limit. What is it for a standard UINT, typically 16-bit?
Usually, yes. 0 up to 65535. And that data type, that specific UINT constraint, is actually incredibly important. It's key to understanding why this block is so robust.
Okay, holding that thought. UINT limit is important. There's one more output, right? Q.
Oh, yes, Q. That's a Boolean output, true or false.
And that tells you.
It tells you if the counter has reached its target. Q becomes true if the current value, CV, is greater than or equal to the preset value, PV.
So if you're counting, say, how many times a hydraulic ram extends to fill a hopper, that Q output going true is what signals, okay, hopper's full, move on.
Exactly that. It's the flag that drives the sequence forward.
All right, that covers the outside. Inputs, outputs, data. But you mentioned the real power. The guarantee is inside, how it behaves.
Yes. Because the ECTU is defined as a basic function block type, its internal operation isn't just, some random code. It's strictly governed by an internal state machine.
The execution control chart, the ECC.
Correct. The ECC is like the director inside the block. When an event input arrives, like R or CU, the ECC looks at its current state and decides which internal piece of logic, which algorithm, to run.
Okay, let's take the simple one first. The R event, the reset, what does the ECC do?
When the R event comes in, the ECC triggers the internal R algorithm.
And the standard is super specific about what that algorithm does, right?
Absolutely precise. The R algorithm is defined as CV, 0, Q, 0.
That's it. CV gets 0, Q gets false.
That's it. 2 assignments happen conceptually together. It wipes the slate clean, sets the count to 0, clears the done flag.
Wow, so simple, but the fact it's defined exactly like that gives you incredible reliability for resetting sequences. No ambiguity.
None. And once those assignments are done, the ETC fires off the RO output event to signal completion, and then it just waits again.
Okay, clear. Now for the main event, literally. The CU count-up event. What happens then?
Right, the CU event triggers the CU algorithm. This is where the actual counting happens.
So the algorithm must be something like CV plus 1 to increment the count, and then it needs to update that Q flag based on the new value compared to PV.
Exactly. The CU algorithm is defined as CV plus 1, Q, CV equal PV.
Increment first, then immediately check if you've hit the target. Makes sense. Standard counter stuff.
It seems standard, yes.
Yeah.
But here's the crucial part, the bit that really shows the engineering thought behind 61499. There's a condition attached.
The condition.
Yes. The ECC doesn't just blindly execute that CU algorithm every time a CU event arrives.
Yeah.
There's a guard condition on the transition to executing the algorithm.
A guard, like a check it has to pass first. What is it?
This is probably the single most important implementation detail of the ECTU. The guard condition is CV 65535.
Wait, CV less than 65535?
65535.
That number again. That's the maximum value for the UINT data type we talked about.
Precisely. The standard is explicitly building in protection against a specific and potentially dangerous failure.
What failure? An overflow.
Exactly. Think about it. What happens if the current value, CV, is already at 65535 and another CU event pulse comes in?
Uh-oh. If it just ran CV hyphy plus 1.
You'd get a numeric overflow.
Yeah.
Depending on the system, that 16-bit register might wrap around back to 0, or worse, it could crash the runtime environment. Imagine that happening on a critical safety sequence on a harvester or an excavator.
Catastrophic. So the guard CV 65535 means?
It means the ECC only allows the CU algorithm to run if the current count is less than the maximum possible value. If CV is already at 65535, the guard condition is false.
So it just stops counting.
It stops incrementing. It effectively hits the brakes right before it would breach that fundamental data type limit. The ECTU will sit at 65535, ignoring further CU events, until an R event comes along to reset it.
That is brilliant. It guarantees defined behavior. It will never overflow. It just saturates safely at the maximum value.
That's the power of defining these things rigorously in the standard. It provides inherent safety and predictability. You know it won't misbehave due to a simple integer overflow.
Okay, that internal guard is a game changer. Let's connect this back to the field. For our listeners tuning in, maybe they're designing controls for, complex implements or construction gear. How does this ECTU compare to the counters they might be used to in, say, traditional IEC 61131 PLCs?
The big advantage, especially in distributed systems, is that precision and reliability we touched on earlier. Your typical 61131 counter, like a CTU block, is synchronous.
Meaning it runs as part of the PLC's scan cycle.
Right. Its logic only gets executed once per scan. Now, if you have a really fast event, maybe from a wheel speed sensor or some quick machine cycle, that pulse could arrive between PLC scans.
And the PLC might miss it entirely or count it late.
Could happen. You might get count jitter or lose counts altogether, especially if the scan time isn't fast enough or varies. Your count isn't truly tied to the event anymore.
Which means if you're tracking something critical, like material flow or total cycles for maintenance schedules, your data could drift and become inaccurate.
Exactly. But the ECTU, being event-driven, reacts when the event happens. That CU pulse triggers the ECC and the algorithm immediately, or at least as soon as the resource it's running on can process it, independent of some global scan time.
So the count is much more tightly coupled to the physical event itself.
Much tighter. And the CUO confirms it happened. This is vital when your control logic is spread out. Maybe some function blocks are on the main controller, others are out on remote I/O modules connected via Fieldbus. You can't rely on a single synchronized scan cycle across all those devices.
Think about something like counting hydraulic cylinder strokes for precise batching. That counting logic might be running right there on an intelligent valve controller out on the machine arm.
Right, what the standard calls a mapped resource. Yeah. And you absolutely need the state, the current count, CV, and the status Q to persist accurately on that remote device.
And the ECTU does persist its state.
Yes, that's fundamental to function blocks. An instance of an ECTU holds its CV and Q values between activations. Even if there's network latency, or the block isn't triggered for a long time, when the next CU or R event arrives, it picks up right where it left off with the correct state.
So it's truly stateful, perfect for tracking things over the long haul, like total operating hours in a specific mode or number of times a safety interlock engaged.
Absolutely. It remembers. And because this behavior, including that vital CV65535 guard, is all defined by the standard, by the ECC logic,
You get interoperability.
bingo. You can design your control application using ECTUs, and you have a high degree of confidence that if you deploy it on hardware from vendor A or vendor B, as long as they comply with the standard, that counter will behave exactly the same way, reliably, robustly.
The ECTU really is like a perfect little example of the whole IEC 61499 idea, isn't it? Packing complex, reliable, standardized behavior counting, state, limits into one neat, reusable block.
It really is. And understanding that internal ECC logic, especially that guard condition, is what separates basic configuration from, well, truly robust automation engineering. You're leveraging the guarantees built into the standard itself.
So the big takeaway for you as you're designing your next piece of heavy machinery control, when you use an ECTU, you're not just getting a counter. You're getting a component engineered to maintain integrity by stopping safely before hitting a fundamental limit.
Which leads to a really interesting question to mull over for your next design review.
Go on.
If the ECTU needs that specific CV65535 guard to prevent a catastrophic overflow that could mess up your whole sequence, where else in your system might you be relying on simpler, maybe cyclic logic that lacks a similar kind of precise event-driven guard? Where else could an unchecked limit cause problems?
That's a great point. Where could failing to check a constraint proactively lead to unexpected behavior, downtime, or even an unsafe condition? Thinking about those proactive checks is really what robust design is all about.
It's that level of defined, guaranteed behavior that the ECTU exemplifies.
Excellent. Well, that's all the time we have for this deep dive into the ECTU. We really hope you now feel ready to use this fundamental IEC 61499 building block with confidence. Thanks for tuning in.